Okay, so this section is about number 3. It's kind of viewing the matrix in a different way. We are going to talk about matrices in terms of the columns. So this one is talk about each matrix. You can view that as some columns. Of course, right? But the nice thing about the viewing that as columns is that if you have a matrix A, looks like this. Just like what you did previously, you have several columns. And you have a vector V. It composed of lots of numbers, C1 up to Cn. And if you watch the preview video, then you will notice that this is exactly equal to, the product of these two is exactly equal to C1 U1 plus something up to Cn Un. And so if you are not so familiar with this part, make sure you watch the video all the time, okay? And a quick example is what you had previously. Say A contains only 2 columns, U1 and U2. And the question wants you to generate something which is 3U1 and 2U2. So of course you have several different ways. For example, one of the group, I think first group, and then extract what is U1 and extract U2 and do this operation. But probably I would just take a vector which is 3 and 2 and multiply by A, then you will get this 3U1 and 2U2. It's not like which one is better, but this is a different point of view. Okay, and you can see that in different groups you also have some other answers. For example, I also see some answer like you want 3 times A 0 0 plus 2A 0 1, and this is the first coordinate. And you also use 3 times A 1 0 plus 2A 1 1. And again, of course, this work, but it will make you take you longer time to type these things. And also it is harder to understand also. Okay, but again, it's not like which one is better. As long as you can make it work, and it doesn't matter. Although sometimes when you are writing the algorithm, one algorithm will be faster than the other, then that matters. But so far, we are not yet got to that point. So I just want to set up a few definitions so that we can talk about that in the future. Let's say S is a set of vectors, and we have a lot of things inside S. It's just a lot of vectors, okay? And you can define what is the span of S. It is all the possible linear combination of S such that C1 up to Cn, all of them are just a real number. Such a thing is called a linear combination, as mentioned in the video. And if you collect all the linear combination, then it is called the span S. So for example, again, you see the picture we had before with the red vector and the green vector. And we can say, for example, S is equal to 2 vectors. Just like this, right? You have 2 vectors and that's all. And if you want one linear combination, then maybe you can take, for example, 3 copies of U1, 3 copies of U1, and then 2 copies of U2. Then you got a vector here. Such thing is called a linear combination. And so if you imagine what vectors are linear combination of these two, then basically it is something that going all along this direction and something all this direction and everything on the plane. So if you only have 2 vectors, then you are likely to generate a plane, and this is called span S. For local students, span means 张开, so you are generating the whole things by just those 2 vectors. Okay, questions here? All right, so this is a kind of important concept in linear algebra. It's not super hard, so make sure you adopt this idea. So the last thing that I want to say is about what we call the column space. So basically, we viewed that before. A times V is a linear combination of columns of A. You take all the columns and then assign some coefficient to that, and then you generate a new vector. And so, if you consider all the things, that looks like A times V, where V can be any possible vectors. Recall that this is like the coefficients. A lot of coefficients stored in V. So A, along with lots of coefficients, it is equal to all the possible coefficients, all the possible linear combinations. Of columns of A. And such a set, we call that as the column space of A. It's the span of all the columns and we called it the column space, denoted by COLA. So each matrix will tell you that, okay, these vectors can be generated and some other vectors cannot, right? So not all the things is in the space.